Alrighty guys, hope you had a nice restful break, and we're going to continue on where we left off before the break. And before the break you had done the distance traveled or total distance traveled worksheet, where you had to find area between a function and the positive x-axis. And what you should have learned is that there's a direct relationship between the area under a curve and the positive x-axis and the definite integral. Okay, so one interpretation is that the area between the curve and the positive x-axis is equal to the total distance traveled for any function. Okay, and what we did is we did rectangle, so we had to partition or subdivide our interval. So this is just the function x squared here that I drew, and it's going from 0 to 1, right? So far what I know is that since this represents the definite integral, my area would be equal to the definite integral from 0 to 1. What goes in here is the function we're integrating, so that'd be x squared dx, right? This tells us we're integrating with respect to the variable x. And if I can integrate that, and I know you can because I already taught you how to work with definite integrals, then I can find the exact area between the curve and the positive x-axis. So what we do is we partition up the area using some number of partitions. So we always let n equal the number of partitions. This is just a refresher. And if I divided this up into n equals 4, let's say 4 partitions, I know that this would be a fourth and a half and 3/4 and then 1. And then I would do a left-hand sum, right? So this is a monotone function, meaning it's strictly increasing over this domain. So if I did a left-hand sum, the interval width, our delta x, the width of our interval from here to here is 1/4, and from here to here is 1/4, and so forth. So we'd say that our delta x is equal to 1/4. And what we would do is, for a left-hand sum, we'd start with the leftmost endpoint of the interval. So when x is 0, we'd go up till we touch the curve and over to draw a rectangle. And this rectangle has an area of 0, right? So it's 1/4 times 0 plus, then we'd go to the next sub interval, which is between x sub 1 and x sub 2. And we'd start with the leftmost endpoint. We'd go up till we touch the curve and over and down, right? And we would continue this process on. So, this is a freehand drawing, so of course my intervals don't look anywhere near the same, but pretend they are, okay? So anyway, the height of the function at 0 is 0. The height of the function here, if this is x1, then the output, the point here is x sub 1 comma f of x sub 1, right? This is x sub 1 comma f of x sub 1. So I may not know the height of the function at this particular point because I don't, this is an arbitrary value. But what I know is that the height at that point is f of x sub 1 plus, and then if I did this one here, this is the point x sub 2 comma f of x sub 2, so it's a fourth. So the area of, so we're finding area, right? And the height of this is 0, and the width is some delta x in this case. Remember that all of our widths are always, in this class, always going to be constant. They're always going to be the same. So if I did n equals to 4, this would really be a fourth, and this would be a half, and this would be 3/4. So it'd be a fourth times f of x sub 1 to get the area of this rectangle, right? And a fourth times 0 to get the area of this rectangle. And a fourth times f of x sub 2 to get the area of this rectangle, and then a fourth, right, this length, a fourth times f of x sub 3. And if I factored out the 1/4 out front like I did, then I could add up the output values for each one of those input values and multiply the result by a fourth, and I would get a left-hand sum. Okay. Likewise, I could do a right-hand sum, and I'm going to use the calculator in a second because I know this is messy. If I do a right-hand sum, my interval widths are not changing, so I'm just going to pull the delta x, or the 1/4, out, And the thing is, if I'm starting with the rightmost endpoint, now I'm starting at x sub 1. And I'm going up till I touch the curve, over and down. So I have 1/4 times f of x sub 1 plus, for this one here, I go over to the rightmost endpoint, go up, over, and down. So, well, let me do it this way. So now the area of this purple rectangle here is f of x sub 2 times 1/4 plus, go to f of x sub 3, over and down, right? F of x sub 3 plus, and then finally I'd go over to 1 and go up, over, and down, and this whole rectangle here would be 1/4 times 1. F of x sub 4 would be 1 in this case, right? This would be x sub 4 here, would be 1. And then I would add all those values together, multiply 1/4, and I'd get the right-hand sum. Remember, because this is monotone, the left-hand sum is going to be an underestimate, because we're going to have gaps in the area. And the right-hand sum is going to be an overestimate, so we're going to have excess area. But what we know is that if we take the sum, if we add the left-hand sum to the right-hand sum, divide by 2. So if we take the average of the left and right-hand sum, then we get a pretty good approximation of the area between the function and the x-axis. Okay? And remember that as we increase these rectangles, so as the width of the interval or the sub-intervals get smaller and smaller, so you know if n were 100 or n were 200 or n were 400, and I had to do 400 rectangles, as n increases, as the number of rectangles increases, then our approximation approaches the exact area between the curve and the x-axis. So what we do with this rectangle approximation is called Riemann sums. We're summing up little rectangles between the curve and the x-axis, multiplying that sum by the width, the interval width, so each subinterval's width, okay? And you know, again, as n is increasing, that's a limiting value, so we can write the limit as the number of rectangles gets bigger and bigger and bigger, or approaches infinity, of the width of our rectangle times the sum of all of the respective heights, then that's equal to the definite integral from a to b of f of x dx. Well, I already wrote that over here, and here it is again, and we know how to integrate this, right? This is just the reverse power rule, so if I integrate this, I'm going to add 1 to the exponent and divide by the same exponent, but then I have to evaluate it from the lower and the upper bound first. So fundamental theorem of calculus, you have to plug in the upper bound first. So 1 cubed is 1 over 3 minus 0 over 3, which is 1/3. So the area between the graph of x squared and the x-axis over the interval from 0 to 1 is 1/3, and that's exact. By the way, I don't want you to forget to use this on your calculator. So if you remember, you're going to hit, let me get out of here real quick. Well, that was terrible. Clear. Alright, so you're going to hit the program key and Riemann 83, hit enter, and then hit enter again. Okay, and the first thing you're going to put in is your function. Okay, so in this case the function was x squared, so I'm going to put in x squared, press enter, and they're going to want the lower bound. Well, the lower bound was 0, press enter, the upper bound was 1. Okay, the number of partitions. So once again, to prove the point, let's just choose 2, right? Now remember, I got an exact, the definite integral is going to give us the exact area, and I got an exact value of 1/3. So let's see how close we are if we just split it into 2 equal intervals. Okay, press enter, and the curve will graph, and if you press enter again, you know, it's going to ask, do you want a left sum? Okay, let's do a left sum. Oops, I pressed the wrong button. 2 is left sum, and it's going to draw the 2 rectangles, and what we see is that our sum is 0.125. Okay, now if I press enter again and I tell it to do a right sum, now it's going to show you, hey, that's a monotone increasing function. The rightmost endpoints of each subinterval are going to result in an overage, and so here we get 0.625, quite a difference between the left-hand sum and the right-hand sum. Okay. If I want to do a midpoint sum, which you did on the exploration, all it's going to do is take the midpoint of each subinterval, go up, so you touch the curve and draw your rectangle. The midpoint sum is 0.3125, and if I click on 6, which is really what I want, the definite integral, I want to know exactly what the area under this curve is. And as you can see, the number of rectangles has increased significantly, and it's 0.333, or 1/3. So again, this is a limiting value. The limit, as the number of rectangles increases, okay, of delta x, which is the width of each one of these little subintervals or partitions, times the height of the function, is going to be equal to the definite integral from a to b of the function that we're working with. Okay? And remember too that I showed you in class, so let me just change the function. If we have some function, say y equals to x, from 0 to 1. So let's see. Settings, I want to change all of them. Okay, so x from 0 to 1. And let's just do 2 partitions again. Okay, there's our function from 0 to 1. If I do 2 partitions, and let's just say a right-hand sum. Again, it's monotone, it's increasing, so the right-hand sum is going to be an overage, and I get 0.75. But what you need to know is that this thing, I'm going to just do the definite integral now. This thing here is a triangle, and you know that the area of a triangle geometrically is 1/2 the base times the height. So guess what? If it's a nice straight line and you can use some geometry, then it's, you know, you can compute it the same way. But this is the function x from 0 to 1. So the area is equal to the definite integral from 0 to 1 of x dx. Well, when we integrate x, we get x squared over 2. And if we evaluate that from 0 to 1, we're going to have 1/2 minus 0 over 2, or 1/2. And as you can see, what came up on the calculator is 1/2. If I go back to, say, a left-hand sum, you see I get a quarter here with just 2 partitions. If I do, if I change the number of partitions to, say, 4, with 2 subdivisions still on a left-hand sum, it gets a little bit better, right? 0.375. And if I change the number of partitions again, 4, let's say 10 partitions. Okay, and again, I'm going to do a left-hand sum. What it does is it subdivides from 0 to 1 into 10 equal subintervals. And notice I'm getting 0.455. I'm getting better. Remember, the definite integral gives us 1/2. So as the number of rectangles increases, then what that means is that we're going to approach the exact area under the curve. So using Riemann sums or using rectangle sums, left and right hand sums in the average, we're going to get a pretty darn good approximation, but here we're going to get an exact an exact value for the area. Okay, and you know, if it's any kind of a smooth curve from A to B, you're going to have to use calculus. You're going to have to use the definite integral. You can't use geometry anymore because you don't know a geometric formula to find the area between this curve and the x-axis. Capiche? Okay, well, we're talking about area above and below. What about, area above. Now what about if we have area below the curve? So let's just suppose for a second, I'm going to keep using this calculator because it'll be an easier visual. So let me change all the settings. And let's just say we're going to use y equals to x. And we're going to go from -2 to 5 with, I don't know, let's just do 7 partitions. So there's our function. Now what I want you to know, let me go ahead and let me just do a left sum. What you're going to notice is here we've got some area below the curve and some area above the curve. The other thing you should notice is that the area below the curve, so from -2 to 0, is much smaller than the area above the curve, or above the positive x-axis and below the function. From 0 to 5, we have a lot more. Okay, so if I get rid of this left sum, I'm just going to do 7 partitions again. What happens is you know, that function, it's hard for the calculator. The calculator doesn't want to, but here's my axis, and here's the line y equals to x. Okay, and my interval that I'm working on is -2 to 5. So I'll call this -2 here, and I'll call this +5 here. The area below is much less than the area above. So what's going to happen is when I take the area below, which area can never be negative, but we assign a negative when it's below the x-axis. We assign a negative, meaning that it's below the x-axis, not that the area is 2. So this is a triangle, right, with a base of 2. And if my function is y is equal to x, when I plug in a -2, I also have a height of 2, right? So the area for this triangle here is 1/2 base times height. Can't have a negative length, all right? And so the area for this little triangle here is 2. Now if I compute this triangle up here, right, when area is 1/2, the length of the base is 5 now, and the height of this, when x is 5, well, if I plug a 5 in, y is 5. So half of 25 is 12.5. So the area up here is 12.5. This area. It's bigger. So what we do to find the net area, just always, oops, I'm sorry. To find the net area, it's always net area is equal to area above minus area below. Area above minus area below. That would be the net area. If I wanted the total area, I would have to change the sign of this. So I know that the area here is 2, but I assign a negative to it because it's below the x-axis. So if I wanted to make it positive, I'd have to flip this part of it above, and I'll show you what I mean hopefully in a second. So I know that seems kind of weird, but I want to show you something. If this is the formula, the area above was 12.5 and the area below was a -2. Okay, remember it's not negative, it's just because it's below. We get is 12.5 plus 2. I'm sorry, my bad, -2. Sorry, minus. So that's going to give us, if we subtract that, 10.5 would be the net area. If I wanted the total area, I would add them together. So I would say 12.5 minus a -2, right? That becomes a plus, so we're going to have 14.5. So by changing the sign of the signed area, that's going to bring this up here and give you the total area. So let me get out of this program here, because you don't want to use that. And if we go to y equals, and we put in our function x and we graph it, and I clearly have, ooh, why isn't it graphing? Because the x, or because the equal sign shut off. Okay, here we go. I clearly have from -2 to 5 in my vision here, so that's good. Okay, so what I can do is I can, from the screen, I can press Math 9, definite integral from 0 to 1 x dx, right? And my calculator will give me, so this is from the home screen, my calculator will give me the exact area. The other thing I could do, because Wait a minute here. Do I have the right function? Oh, I put the wrong. I'm sorry, guys. Let's try this again. My definite integral was wrong. So, math 9 from -2 to 5 of x dx, and I get 10.5. Okay, so what the calculator is doing, it's subtracting out the area below, like you see in the picture, and you're getting this net area here. So the calculator is going to subtract out this area below from the area above. Now, if this area would have been bigger below and the area above would have been smaller, then you would end up with a negative value, and that's fine. It just means it's most of the area is concentrated below the x-axis. Okay, so sorry about that. I had put in the wrong limits initially. If I want the total area of this thing, then what I have to do is I have to graph the absolute value of the function. So that's just math right arrow 1. Okay, and I'm going to put an x in there. Okay, now if I graph that, graphing that is taking all the area below and bringing it above the x-axis. So now if I want to find my total area, I'm going to take that absolute value, I'm going to press second calc, and I'm going to press 7. Second calc 7 from -2 to 5. That's my lower and upper bounds. And what the calculator is going to do is shade that in from -2 to 5. And you can see that the total area is 14.5. So your calculator doesn't find total area all by itself. It will if you input the definite integral on the home screen like I did a minute ago, like this. That'll give you the exact area between the curve and the x-axis. But remember, it's going to give you the net area. If you want the total area, in this case here, because some area can be below, you're going to have to use the absolute value function so that the calculator knows what to do. Okay, and there's a good example of that on page 173. So let me do that example. The integral on 173 goes from 0 to 3, and the function is 3 minus x dx. Now I know this is a linear function with a slope of -1, and so do you. And if if I wanted to sketch it, I could do that real easy, right? This is just a vertical shift upwards of 3 units. So when x is 0, y is 3, so this graph's going to look something like this. And from 0 to 3, well, 3 might be here, it might not. If I plug in a 0, I'm going to have 3. If I plug in a 3, I'm going to have 0. So it's going to be a triangle, and I could say, hey, the area is 1/2 base times height, and I could find it that way. However, there is going to be a little region. If we change this to say a 5, then there's going to be this little region below the x-axis. We'll call that 5 there. Okay, so from say 0 to 5. And sometimes these areas cancel each other out and you get a 0 area too, by the way. So anyway, let's just look at this. Let's look at 0 to 5, 3 minus x dx. I want to know the net area under the curve. Well, we said that the net area is equal to area above minus area below. And essentially all I have to do is plug that thing in to my calculator, so I'm going to do that. Right, I'm going to go to y equals. I like using y equals, you don't have to, but I like the visual on it. So the function is 3 minus x. I'm going to hit the graph key, and there's our function. Okay, and what I'm going to do is I'm going to do second calc 7 from 0 to 5, lower bound to upper bound, and you see the calculator shading, and I'm going to get a net area of 2.5. So I don't know if you can see that good, sorry about that. So net area of 2.5. So if I just plug this thing in, that's my net area. If I want the total area, the only thing I have to do is go back and replace this thing with, put it inside absolute value. So math right arrow 1, and it was 3 minus x. Now if I graph it, you see it pulls all the points of the line below the x-axis above. And now if I do second calc 7 from 0 to 5, Then it's going to add all the areas above, and you see it's much different at 6.5. So quite a difference. Total area, you're going to have to take the absolute value of f of x. Okay? And the total area there was much greater in this case. It was what, 6.5. Now how would you write the integral for that? Easy. Okay, you would have to tell the grader, this is the integral I want total. Okay, so I need to be specific. Total area is equal to the definite integral from 0 to 5, absolute value of 3 minus x dx. That tells the grader that you understand that the calculator takes net area automatically, and that you have to input the absolute value in order to come out with the correct answer. And you would say that this is equal to 6.5. If they asked you for the net area, you would write down this integral, and of course the calculator automatically gives you net area, so no big deal. Okay? Now what if we had to do this without a calculator? Easy peasy. If I wanted the net area, so let me move this because this is messed up. If I wanted net area, that's the integral from 0 to 5 of 3 minus x dx. How do I integrate this by hand? Well, I get 3x minus x squared over 2, and I've got to evaluate that expression from 0 to 5, right? So that's going to give me 3 times 5 minus 5 squared over 2, evaluated at the upper bound, minus, and luckily we're going to have a 0 here, so this whole second term is going to go away, but it'd be 3 times 0 minus 0 over 2. Okay, so here we're going to have 15 minus 25 halves. I'm doing a terrible job tonight. I'm sorry, guys. Minus 0. So I really just need to focus on this. 2 times 15 is 30 minus 25 over 2 is going to give me 5 halves. And that's about 2.5. And that's exactly what we got above here when we let the calculator do it for us. Okay, so right now we're going to use the calculator a lot to find the area, just so you can kind of get used to it, but very, very soon we're going to have to start doing it by hand, and the functions that you're going to have to integrate are going to become increasingly complex. In other words, you're going to have to use, U substitution to find the original function so that you can evaluate it from A to B and so forth. So what you're going to do today is you're going to get used to using the calculator, and I've assigned page 176, 1 through 15 odd, and I want you to just follow the instructions. All right, I'm giving you the odds so you can check Bob in the back of the book to make sure that you're getting the right answers, and use your calculator. And if you're asked to do left, right-hand sums, that kind of thing, then make sure you use your program for that. Once again, it's program Riemann 83, and hit enter, and then hit enter one more time, and that'll take you in, and then you can just, just don't forget to press enter after everything you entered, so I don't know, like x squared. Nothing's going to happen unless you press enter again, so that way you can input the lower and the upper bounds and the number of partitions that you want. Okay, so you're going to do those, and if you have any questions or you get stuck on any of the problems, let me know what problems you want me to go over, and I'll make a follow-up video and I'll do those problems just like I do at the start of every class when I ask you, which problems you want to cover. And I'll do it step by step, and I'm a little bit tired right now, so again I apologize for not moving my paper and kind of rambling a little bit, but I will make sure that I do it step by step and keep it in the viewing screen, so that way I'm not going off the page in the video. Okay, so anyway, I hope this helps. I hope this brings back memories before your break. And remember, don't forget to let me know if there are any questions on any of the problems. If you get stuck, let me know, and I'll be more than happy to help. Okay? So I'll see you next class. Have a good night. Bye.